Have you heard that black holes are cosmic vacuum cleaners that never let anything escape? That's the misconception. In reality, black holes can leak, not by swallowing first and then belching out matter, but by emitting radiation from their event horizon as if they had a temperature. And here's the part that sounds like science fiction. The colder the black hole gets, the faster it can lose information, because the heat it emits changes the rules of its own entropy bookkeeping. So the question isn't just, do black holes radiate? It's, how does that radiation drive an entropy runaway? If you've ever wondered why entropy in extreme spacetime behaves like a feedback loop instead of a one-way arrow, Hawking radiation is the key. And it's one of the few windows we have into the quantum nature of gravity. Before Hawking, the classical picture of black holes was clean and ruthless. Based on general relativity, once matter crossed the event horizon, it couldn't come back. Black holes were defined by geometry, not thermodynamics. They had mass, charge, and angular momentum, but no obvious temperature. Yet physicists noticed a strange parallel. The area of a black hole's event horizon never decreases in classical processes, like a version of the second law of thermodynamics. In the 1970s, Jacob Bekenstein proposed that horizon area should be linked to entropy. If that was true, then black holes weren't just sinks, they were thermodynamic objects. The puzzle was dynamical. What would cause them to increase or decrease their entropy, especially once you allow quantum fields to exist outside their horizons? That question sat waiting for an argument that was not just poetic analogy, but calculation. The core mechanism begins with quantum fields near the horizon. In empty space, quantum theory insists the vacuum is not truly empty. It's full of fluctuations, pairs of particles and antiparticles that can appear briefly. For a distant observer, the event horizon changes what pair means because the horizon acts like a one-way boundary for information and trajectories. Hawking's insight was to treat the quantum fields on a curved spacetime background and track how modes, possible wave patterns of those fields, propagate in the presence of a horizon. What emerges is that what looks like vacuum to a freely falling observer near the horizon can look like a thermal state to a faraway observer. The result is Hawking radiation. Black holes emit particles with a spectrum corresponding to a temperature proportional to the surface gravity. Smaller black holes have stronger surface gravity, so they are hotter. Now connect that to entropy runaway. The entropy of a black hole in the centipairical picture scales with horizon area, which scales with the square of the black hole's mass. But Hawking radiation reduces mass. As mass decreases, horizon area decreases, meaning the black hole's own entropy should drop. However, the radiation carries entropy away too. And because the radiation is thermal, it carries a lot of entropy for each unit of energy emitted. The net effect is subtle but crucial. The combined system can obey a generalized second law, where total entropy never decreases when you include both the black hole and the emitted radiation. Here's the feedback loop. A black hole emits radiation, which costs energy, so its mass shrinks. Shrinking mass increases its temperature, because temperature is inversely related to mass. Higher temperature means more radiation power, because hotter black bodies radiate faster. More radiation means mass drops even further. That's the acceleration. The emission rate grows as the black hole gets lighter. Entropy runaway follows the same logic in the thermodynamic ledger. As the black hole evaporates, the horizon area shrinks rapidly, while the radiation entropy grows, and the relative contributions evolve in a way that amplifies the evaporation process. In simple terms, Hawking radiation doesn't just subtract entropy. It reorganizes the entropy flow so that evaporation hastens, and the thermodynamic accounting keeps accelerating toward the final, highly quantum stage. This runaway matters because it challenges how we think about information and the end of time. If a black hole evaporates completely, what happens to the information about the matter that fell in? Classical intuition would suggest it's lost behind the horizon forever. But the radiation is not random. Quantum theory implies it must carry correlations. The existence of Hawking radiation triggered decades of debate about whether evaporation destroys information or preserves it in subtle quantum correlations. The concept of entropy is at the center of this. Entropy measures uncertainty, but in quantum mechanics, uncertainty can be entanglement. If Hawking radiation is entangled with the remaining black hole, then as the black hole shrinks, the entanglement structure must change dramatically. That's why modern developments, like the page curve and holographic ideas, try to reconcile the thermodynamic behavior with unitary quantum evolution. In other words, Hawking radiation isn't just a trickle, it is the test case for quantum gravity. Even beyond black holes, the mechanism shows how horizons behave like thermodynamic objects. It tells us that gravity, space-time geometry, and quantum fluctuations are not separable ideas in the deep regime. The same kind of reasoning, quantum fields in curved backgrounds producing thermal behavior, has analogs in condensed matter systems and laboratory horizon analogs, strengthening the idea that the phenomenon is not a one-off mathematical accident. And philosophically, the entropy runaway forces a confrontation with what the universe is doing at its most extreme. The arrow of time, often linked to entropy increase, becomes a question of how space-time itself encodes uncertainty and information. So where does this leave us? We started with a simple misconception. Black holes don't just swallow, they leak. Hawking's calculation showed that horizons convert quantum vacuum fluctuations into thermal radiation seen by distant observers. Because the temperature rises as the black hole mass falls, the evaporation accelerates, an entropy-involved feedback loop. The generalized second law keeps the bookkeeping consistent, but it doesn't settle the deeper question: how information survives the final act. The entropy runaway is both a thermodynamic story and a quantum gravity signal. It tells us that the end of a black hole is not a quiet disappearance into oblivion, but a chaotic quantum exchange between geometry and fields. And perhaps the most unsettling implication is this: what we call a horizon may be less like a wall and more like an engine, turning the structure of space-time into temperature, entropy, and maybe answers. If you want more on how the universe turns contradictions into laws, subscribe for more.